The astonishing fact that NASA's Interstellar Mapping and Acceleration Probe, IMAP, is designed to capture the most detailed glimpse of the solar wind ever observed, revealing secrets about the boundaries of our solar system. This completely changes how we understand the dynamics of our cosmic neighborhood, particularly in conjunction with the Carruthers Geo-Corona Observatory and NOAA's Solar Wind Forecasting Observatory, SWFOL1. Here's what scientists actually discovered. As we dive into the depths of space exploration, the interplay between solar activity and our planet's atmosphere becomes an engaging narrative woven with intricate scientific threads. The IMAP mission, launched by NASA, is not just another satellite. It promises to transform our understanding of how the solar wind interacts with Earth's magnetic field. Imagine a scenario where scientists can finally decode the mysteries of cosmic particles that travel billions of miles, influencing everything from satellite operations to climate patterns on Earth. The IMAP will take its position between Earth and the Sun at the Lagrange point 1, L1, a point in space that offers a stable vantage point for monitoring solar activity. But what is truly exhilarating is the way it will pair its findings with the Carruthers Geo-Corona Observatory, located in Puerto Rico, which has been pivotal in studying the geocorona, the outermost layer of Earth's atmosphere that glows with hydrogen. This glowing halo is a direct result of solar radiation interacting with our atmosphere, and understanding it can tell us not only about the solar wind's composition, but also about the dynamics of space weather and its effects on our planet. To put this in perspective, let's explore the fascinating history of these observatories and how they contribute to a better understanding of the solar system. The Carruthers Geo-Corona Observatory has been crucial since its inception, providing scientists with a unique look at the interactions between solar particles and the Earth's atmosphere. With the recent advancements in technology and collaboration with IMAP, the geocorona's study has entered a new era of precision. Researchers now find themselves in a position to unveil the nuances of these interactions with an unprecedented level of detail. Now, let's address some of the popular myths surrounding solar activity and space weather. For instance, one common misconception is that solar wind is a constant and unchanging stream of particles. In reality, it is dynamic and can vary greatly in intensity and composition. This variability can lead to fascinating phenomena, such as geomagnetic storms, which can disrupt GPS systems, satellite communications, and power grids. The data collected from both IMAP and the Carruthers Geo-Corona Observatory will provide empirical evidence to better understand these fluctuations, allowing scientists to create more accurate models for predicting solar activity. The collaboration with NOAA's SWFOL1 adds another layer of understanding to this cosmic puzzle. The SWFOL1 is primarily focused on real-time monitoring of solar wind and solar flares, giving scientists the ability to provide timely forecasts concerning space weather. Imagine having the capability to predict a solar storm days in advance. This is not merely science fiction. It's an imminent reality thanks to advancements in our observational technologies and methodologies. Recent findings indicate that the solar wind does not just affect space, it also has far-reaching impacts on our terrestrial environment. For example, during intense solar events, increased radiation levels can have effects on satellite technology and even pose risks to astronauts in space. Understanding the mechanisms through which solar wind interacts with Earth's magnetosphere is crucial not just for space exploration, but also for safeguarding our technological infrastructure. As we dissect the methodologies employed by scientists at these observatories, it becomes clear how modern tools and techniques are reshaping our understanding. The instruments aboard NASA's IMAP are equipped with cutting-edge technology designed to measure various aspects of the solar wind, including its speed, density, and temperature. These measurements will help researchers paint a complete picture of how solar material travels through space and impacts our atmosphere. Furthermore, the geocorona itself is a treasure trove of information. Observing the geocoronal hydrogen glow allows scientists to glean insights into the dynamics of Earth's atmosphere as it interacts with solar radiation. The interplay between these two systems gives clues not only to past climatic conditions, but also provides a baseline for understanding future changes. What is striking about these efforts is how they connect back to ancient knowledge. Indigenous cultures often had their own interpretations of celestial patterns and solar phenomena long before modern science unraveled the mechanics behind them. By juxtaposing ancient understanding with cutting-edge science, we begin to appreciate the continuity and evolution of our knowledge of the cosmos. In a world where technology often overshadows nature, these missions remind us of our place within the universe. As the IMAP, Carruthers Geocorona Observatory, and SWFOL-1 work in concert, they are not merely gathering data. They are weaving a narrative that transcends time, linking ancient wisdom with modern discoveries. As we continue to explore the implications of these findings, we'll delve deeper into some of the most astonishing discoveries that have emerged from this realm of solar physics. From the intricacies of magnetic reconnection that can unleash immense energy in the form of solar flares, to the role of cosmic rays in atmospheric chemistry, each revelation paints a more detailed portrait of our solar system and its ongoing story. Now, before we move on to explore some of these breathtaking discoveries, let's take a moment to reflect on what we've learned so far. The collaboration between NASA's IMAP and observatories like Carruthers and SWFOL-1 represents a significant leap forward in our understanding of space weather and its effects on Earth. Each piece of data they collect not only enhances our scientific knowledge, but also emphasizes how interconnected our universe truly is. In the next segment, we'll delve into the fascinating mechanics of solar flares and how they can impact life on Earth in profound ways. But first, let's take a moment to appreciate the incredible journey of discovery unfolding in the realms of our solar system. Stay tuned as we continue to unravel the mysteries of our universe. End of Part 1, to be continued in Part 2. Did you know that the vast invisible bubble around our planet, known as the geocorona, extends millions of kilometers into space and is primarily composed of hydrogen? This completely changes how we understand the Earth's atmosphere and its interaction with the solar wind. Here's what scientists actually discovered about the geocorona through NASA's IMAP and the Carruthers Geocorona Observatory, and how NOAA's SWFOL1 is enhancing our understanding of this phenomenon. We embark on this scientific journey. Let's dive deeper into the implications of the geocorona. The geocorona, which forms the outermost layer of the Earth's atmosphere, plays a critical role in shielding our planet from harmful solar radiation. It also influences the dynamics of space weather and has implications for satellite operations and communication systems. Imagine living in a house with a magnetic shield that protects you from cosmic rays. That's essentially what the geocorona does for Earth. NASA's Interstellar Mapping and Acceleration Probe, IMAP, has recently taken center stage in unraveling the intricacies of this region. Launched with the ambition of understanding the heliosphere, the bubble of solar wind and magnetic fields that envelops our solar system, IMAP's mission is to capture the elusive particles that interact with the geocorona. What's particularly fascinating is how IMAP will help scientists to clarify the boundaries of the heliosphere, revealing connections to cosmic phenomena that have puzzled astronomers for centuries. But how does this relate to ancient cultures? Well, many civilizations observed celestial events and phenomena without the benefit of modern technology. They created myths and legends that often reflected their understanding of the cosmos. For example, ancient Egyptians revered the sun, personifying it as the god Ra. Their pyramids even align with the stars, showcasing an impressive grasp of astronomy that, while not scientific in the modern sense, reveals a cultural link to the cosmic patterns we are now decoding with advanced technology. Turning our gaze back to modern science, the Carruthers Geocorona Observatory has been pivotal in measuring the brightness of the geocorona. Using sophisticated ultraviolet imaging techniques, it provides invaluable data on the hydrogen atoms that constitute this atmospheric layer. Interestingly, the observatory's findings challenge some earlier misconceptions about the density and behavior of hydrogen in the geocorona. Previous models suggested that the geocorona was much less reactive than it actually is. The more we observe, the more we realize that our understanding of this region is still evolving. Moreover, the work done at the Carruthers Observatory underscores the importance of interdisciplinary approaches in modern science. By integrating methodologies from astrophysics, atmospheric science, and even ancient history, researchers can create a more holistic view of the Earth's place within the solar system. This synergy of knowledge not only enriches our understanding of the geocorona, but also highlights the beauty of scientific inquiry as a continuum from ancient wisdom to cutting-edge technology. Now, let's consider the NOAA Solar Wind and Magnetospheric Observatory, SWFOL1, positioned at the first Lagrange point, a region in space where the gravitational forces of the Earth and the Sun balance. SWFOL1 serves as a sentinel for solar wind and magnetic field observations. This positioning allows for real-time data collection about solar activities, including coronal mass ejections, CMEs, that can have profound effects on our planet. For instance, a large CME can disrupt power grids, satellites, and even GPS systems. In a way, SWFO L1 acts as a kind of cosmic weather station, detecting disturbances in solar activity, much like meteorologists track storms on Earth. This innovative approach underscores how our modern understanding of the cosmos allows us to prepare for and mitigate the impacts of space weather. Yet this knowledge doesn't just benefit contemporary society. It also resonates with ancient practices. Civilizations such as the Maya meticulously tracked celestial events, understanding that solar cycles influenced agricultural success. Their observations laid the groundwork for what we now recognize as an early form of astrophysical science. Bridging the past with the present, it's remarkable how ancient knowledge informs modern research. For instance, the Maya's intricate calendar system was based on celestial patterns, including the movement of the sun and moon. These observations were not mere superstition, but reflections of their environmental realities. Their awareness of celestial phenomena parallels the scientific methods employed today, highlighting a thread of continuity that runs through human inquiry. The interplay of culture and science invites us to consider the implications of our modern technological advancements. For example, with tools like IMAP and the data streaming from SWFO L1, we can now track solar activity with unprecedented precision. This capability allows us to make predictions about space weather events that can affect everything from satellite communications to power infrastructure on Earth. But it also begs the question: how can we ensure that this knowledge is used responsibly and ethically? As we delve deeper into the scientific patterns revealed by these observations, it becomes clear that our understanding of the universe is an ever-evolving narrative. For instance, the interactions between solar wind and the geocorona create a complex dance of particles and electromagnetic fields. This interplay not only protects our atmosphere, but also shapes the very conditions that allow life to thrive on Earth. Isn't it astounding to think that the same forces that govern the universe also provide us with the air we breathe? To appreciate the significance of these discoveries, we must consider the archaeological methodologies that illuminate our understanding of ancient cultures. Excavations and analyses of historical sites often yield artifacts that reveal how ancient peoples interacted with their environments. In many cases, these findings echo modern scientific discoveries, showcasing humanity's long-standing connection with the cosmos. For instance, researchers have unearthed ancient tools and inscriptions that indicate the level of astronomical knowledge possessed by civilizations like the Babylonians and the Greeks. Such discoveries help bridge the gap between myth and reality, demonstrating that humanity has been striving to understand the heavens for millennia. Moreover, the tools of modern archaeology, such as carbon dating and remote sensing technology, allow us to reconstruct the past with greater accuracy than ever before. By applying these techniques, scientists can create timelines that not only reveal how cultures evolved, but also how they adapted to changes in their environments over time. This adaptability is a testament to human resilience and ingenuity, characteristics that have allowed our species to thrive in diverse conditions. As we piece together these historical narratives, we gain insights into the patterns of human behavior and understanding through the ages. The ancient Greeks, for example, were not only philosophers, but also astronomers who sought to explain the motions of celestial bodies. Their work laid the foundation for modern astronomy and physics, paving the way for future thinkers like Copernicus and Galileo. This lineage of thought exemplifies how knowledge is built upon, evolving through dialogue across generations. Yet, misconceptions about ancient knowledge often persist. Some might assume that early civilizations lacked the sophistication to observe and interpret astronomical phenomena accurately. However, as modern discoveries reveal, many ancient cultures had a profound understanding of the cosmos, often using their knowledge for practical purposes such as navigation and agriculture. Consider the Polynesians, who navigated vast oceans without modern tools, relying instead on their observations of the stars, wind patterns, and ocean currents. Their mastery of celestial navigation is a testament to the incredible potential of human observation and understanding. In a similar vein, our current scientific explorations are not free from misconceptions. For instance, the idea that space is a perfect vacuum has been challenged by the discovery of various cosmic particles that permeate even the emptiest regions of space. The work of IMAP and SWFO L1 is crucial in mapping these particles and understanding their implications for space weather and planetary health. This ongoing inquiry not only reshapes our understanding of the universe, but also illuminates the interconnectedness of all things, a principle deeply ingrained in many ancient philosophies. As we continue to explore the relationships between culture, science, and the cosmos, we unveil new layers of meaning and understanding. The patterns that emerge from the data collected by modern instruments like IMAP and NOAA's SWFO L1 reflect a complex interplay of forces that have shaped our planet and its history, much like the stories woven into the fabric of human culture. Through this lens, we can appreciate the elegance of scientific inquiry as a pathway to wisdom. Each discovery feeds into a larger narrative, each observation a thread in the tapestry of understanding that connects the ancient to the modern. As we forge ahead, let's remain curious and engaged, asking questions and seeking answers that resonate across time, ensuring that our explorations of the universe not only illuminate the secrets of the cosmos, but also honor the rich legacy of those who came before us. In the next chapter of our journey, we will explore even more fascinating connections between ancient knowledge and modern science, uncovering how historical practices continue to influence current scientific paradigms. We'll delve into the methodologies that bring ancient discoveries to light and how they reshape our understanding of the past, revealing the remarkable patterns that emerge as we bridge the temporal divide. Join me as we continue to unravel this extraordinary story of humanity's quest for knowledge among the stars. Did you know that our atmosphere extends far beyond where most of us ever think to look, reaching out into the vast expanse of space where it interacts with solar winds and cosmic rays? This completely changes how we understand our planetary environment and its relationship with the cosmos. Here's what scientists actually discovered with projects like NASA's Interstellar Mapping and Acceleration Probe, IMAP, and NOAA's Space Weather Follow-on Lagrange 1 SWFOL-1 missions, as well as the groundbreaking work happening at Carruthers Geocorona Observatory. To grasp the significance of IMAP, let's take a step back and consider the history of our understanding of the Earth's atmosphere. For centuries, ancient civilizations attributed the phenomena surrounding them to divine beings. Weather patterns were often seen as the whims of gods, and celestial events were interpreted as omens. The Greeks, for example, believed in a pantheon where each god held sway over different natural forces. Yet, it wasn't until the advent of scientific inquiry that humanity began to peel back the layers of myth and superstition surrounding our planet. The traditional narrative of the cosmos was fundamentally altered with the introduction of the scientific method. Fast forward to today, where our scientific understanding has evolved dramatically. We now know that Earth's atmosphere is not a static shell, but a dynamic, ever-changing space filled with gases and particles that interact with solar radiation. The IMAP, launched in 2025, aims to explore this region where solar winds collide with the Earth's magnetic field. One of the primary goals of IMAP is to map the interstellar medium and how it influences the heliosphere, a vast bubble surrounding the solar system filled with solar wind, and in doing so, it reveals deeper truths about our cosmic neighborhood. Now let's delve into the fascinating ways that modern science is reshaping our understanding of the past. The IMAP will collect data that helps clarify how solar winds affect our atmosphere, and conversely, how the Earth's magnetosphere protects us from harmful cosmic radiation, an interplay that has been essential for the evolution of life on our planet. This mission builds on centuries of astronomical studies, proving that ancient observations of celestial phenomena can have modern scientific applications. For instance, the ancient Babylonians meticulously recorded planetary motions, which could now be compared against the data collected by IMAP to enhance our understanding of cosmic cycles. But it isn't just NASA that is contributing to our understanding of the atmosphere and beyond. The NOAA SWFOL-1 mission plays a crucial role in monitoring space weather, tracking solar flares and coronal mass ejections that can disturb the Earth's magnetic field. These solar events can cause power outages, satellite damage, and even affect communication systems. By understanding these phenomena, we can better prepare for the unintended consequences of our star's activity, which echoes the fears of ancient societies who interpreted solar storms as divine punishment. Furthermore, the Carruthers Geocorona Observatory stands as a sentinel for atmospheric study. Located at the edge of space, this observatory is uniquely positioned to observe the geocorona, an outer layer of the Earth's atmosphere where hydrogen particles reside. Through its observations, researchers can measure how these particles interact with solar winds, shedding light on the processes that govern atmospheric escape and the long-term evolution of our planet. This observatory underscores the importance of scientific methodologies, like spectroscopy, that allow us to interpret the spectral signatures of light emitted by these particles, revealing the composition and dynamics of our atmosphere. Take a moment to consider the implications of these discoveries. By understanding how our atmosphere interacts with the cosmos, we not only gain insights into Earth's climate and weather patterns, but also uncover the fundamental processes that dictate the evolution of planetary atmospheres across the universe. This is an exciting time in the realm of space science, as we bridge the gap between what ancient civilizations speculated about the heavens and the empirical evidence we gather today. As we reflect on the profound connections between ancient knowledge and modern discoveries, it's fascinating to see how ancient cultures viewed comets and eclipses as harbingers of change. The ancient Chinese, for instance, meticulously documented solar eclipses, using these events to predict societal upheaval. Fast forward to present-day astronomy, and we know that solar eclipses result from specific alignments of celestial bodies, an understanding grounded in mathematical precision that ancient cultures could only glimpse at. These remarkable intersections of knowledge illustrate how science transcends time, allowing us to build on the foundations laid by those who came before us. The patterns observed in nature, whether they be the cycles of the moon or the phases of the sun, are constants that link our past to our present. The data collected by IMAP and spectroscopy L1 will allow scientists to draw parallels between past solar behaviors and modern implications, ultimately enhancing our understanding of how our planet operates within the broader solar system. Moreover, let's consider the methodologies employed in these scientific endeavors. With each mission, researchers employ advanced technologies and analytical techniques to unravel the complexities of our atmosphere. For example, the use of high-resolution imaging and data collection tools at the Carruthers Geocorona Observatory allows scientists to visualize the geocorona in ways that were previously unimaginable. The observational data is then compared against advanced models to predict atmospheric behaviors, creating a dynamic feedback loop that enhances our understanding of atmospheric science. What's truly awe-inspiring is how these missions have the power to reshape misconceptions about our atmosphere. For many years, it was considered that the Earth's atmosphere was a straightforward boundary that simply separated us from space. However, as we gather more data through missions like IMAP and SWFOL1, we can illustrate how the interactions between solar winds and the Earth's magnetic field create a protective shield, enabling life to flourish. By debunking the myths surrounding the thinness of the atmosphere and emphasizing its dynamic nature, we inspire a deeper appreciation for the complexities of our planetary environment. As we continue to explore these scientific wonders, one begins to appreciate how interconnected our universe truly is. The very particles that escape our atmosphere can provide us with clues about the origins of our solar system and the formation of planetary bodies. This interplay between Earth's atmosphere and the broader cosmos presents a tantalizing mystery that scientists are eager to unravel. Looking ahead, the future of atmospheric and space weather research is incredibly bright, with cutting-edge missions paving the way for novel discoveries. Imagine what we might learn about other worlds and their atmospheres as we expand our understanding of how solar interactions shape planetary environments. By studying the geocorona here on Earth, we may find parallels with exoplanets where conditions support life, or perhaps uncover atmospheric features that challenge our existing theories of planetary formation. In essence, these scientific endeavors serve a dual purpose. They not only expand our knowledge of our own planet, but also set the stage for interstellar exploration. Understanding the atmospheric dynamics of our own world equips us with the knowledge needed to search for habitable conditions elsewhere in the universe. The quest for knowledge is unending, and as we decode the mysteries of the cosmos, we build a bridge between the ancient cultural practices that sought to explain the heavens and the rigorous scientific methodologies that illuminate our path today. As we progress through this ongoing exploration, it's worth pondering the profound implications of our findings. Each new discovery has the potential to reshape the way we perceive our place in the universe. We are not mere observers of the cosmos. We are participants in a grand exploration that transcends time and space. As we gather insights, we become part of a continuum of knowledge that connects us with generations past, while simultaneously paving the way for future explorations. The interplay of science, history, and culture reveals a tapestry of understanding that is rich and multifaceted. From the ancient practices of observing celestial events to the cutting-edge methodologies employed in modern space weather research, we see that the quest for knowledge is a universal human endeavor. Through the lens of projects like IMAP, NOAA's SWFOL-1, and the Carruthers Geocorona Observatory, we uncover new dimensions of understanding that not only create a sense of wonder, but also inspire us to ask deeper questions about our universe. What does all this mean for us today? It challenges us to think critically about the information we receive and to appreciate the processes that allow us to uncover the truth about our environment. In a world where misinformation can spread easily, understanding the scientific process and the evidence behind discoveries is more crucial than ever. By recognizing the importance of rigorous scientific inquiry, we can foster a culture of curiosity and respect for knowledge that transcends disciplinary boundaries. So, as we continue to delve into the mysteries of our atmosphere and beyond, let us remain curious and open to the wonders that await us. The journey of discovery is just beginning, and with each revelation, we come closer to grasping the intricate relationships between our planet, the sun, and the cosmos. And that, dear friends, is a mystery worth exploring. In our next segment, we will delve deeper into the latest findings from these missions and explore how they impact our understanding of the solar system and beyond. Stay tuned as we unravel the secrets of the universe, one discovery at a time. Did you know that there's a vast, invisible shell surrounding our planet that plays a crucial role in protecting us from cosmic radiation and solar storms? This protective layer is known as the Earth's geocorona, and its secrets are being unraveled by groundbreaking missions like NASA's Interstellar Mapping and Acceleration Probe, IMAP, and the Carruthers Geocorona Observatory. This completely changes how we understand not just our atmosphere, but also the immense interplay between solar winds and Earth's magnetic field. Here's what scientists have actually discovered: the invisible armor. Understanding the geocorona. To grasp the significance of the geocorona, we must first understand what it is. The geocorona is a thin, hydrogen-rich layer that exists in the upper atmosphere, extending thousands of kilometers into space. It acts as our first line of defense against the relentless bombardment of solar wind, a stream of charged particles emitted by the sun. Historically, the concept of a protective layer surrounding the Earth was often dismissed, leading many to believe that the atmosphere ended abruptly. However, recent studies have revealed that this geocorona is not only vast, but dynamic, reacting to changes in solar activity in ways that were once unimaginable. Data from the IMAP mission, scheduled to launch later this year, aims to provide a comprehensive understanding of this remarkable structure. By mapping space weather phenomena and their interactions with the geocorona, scientists hope to illuminate how these interactions affect satellites and communication systems on Earth. The interplay between solar radiation and our atmosphere has profound implications for technology, agriculture, and even climate patterns. From the Babylonians to the Mayans, observed the sun and stars, attributing significant meaning to solar phenomena. Solar eclipses, for example, were often seen as omens, eliciting fear and reverence. However, we now recognize these occurrences as natural events that can be predicted with precision through celestial mechanics. Fascinatingly, some indigenous cultures had an astonishingly accurate understanding of cycles and patterns, supported by observational astronomy. The Dogon people of Mali, for instance, had knowledge of the Sirius star system that astounds modern astronomers. Their understanding of Sirius B, a companion star, predates its discovery by Western astronomers by centuries. This raises an intriguing question. Could there be additional ancient knowledge about the geocorona or other atmospheric phenomena waiting to be uncovered? Carruthers Geocorona Observatory, a window into the past. Enter the Carruthers Geocorona Observatory, a specialized facility designed to study the geocorona and its interactions with solar winds. Located atop the spectacular Mount Haleakala in Hawaii, the observatory boasts remarkable clarity and is an ideal vantage point for astronomical observations. One of the most fascinating aspects of this observatory is its focus on ultraviolet light, which is pivotal for understanding the geocorona's composition and behavior. Scientists have employed sophisticated spectroscopic techniques to analyze UV emissions from the geocorona. This approach not only reveals the abundance of hydrogen atoms in the geocorona, but also how these atoms interact with solar wind particles. The observatory has collected invaluable data that sheds light on the processes that govern the dynamics between the sun and Earth, contributing to our understanding of space weather. Among the findings, researchers have noted that the density of the geocorona fluctuates significantly during solar storms. This observation challenges prior misconceptions that the geocorona remains static. Instead, it reveals a complex and responsive environment that plays an active role in modulating space weather effects. Bridging ancient knowledge and modern discoveries. What's truly captivating is how ancient civilizations might have perceived events that modern science is only beginning to understand. The concept of sky gods in various mythologies may have been early interpretations of the sun and celestial bodies' influence on Earth. This interplay between the heavens and human life showcases an ancient awareness of the cosmos that resonates with current scientific endeavors. As we plunge deeper into the cutting-edge research of the IMAP and the Carruthers Observatory, we find ourselves in uncharted territory, where ancient wisdom and modern science align. For instance, the way the geocorona interacts with solar particles is reminiscent of the ancient beliefs that celestial events could influence earthly occurrences, from weather patterns to crop yields. These connections remind us that the quest for knowledge is both a modern and ancient endeavor. Modern scientific methodologies and findings. Delving into methodologies, the scientific process plays a vital role in piecing together the complex puzzle of our atmosphere. The use of advanced imaging technologies and satellite-based observations has revolutionized our understanding of atmospheric science. IMAP's suite of instruments will not only map the geocorona, but also analyze the particles and fields that flow through this region of space. One of the critical methodologies used in these studies is the application of remote sensing techniques, which allow scientists to gather data from afar without disturbing the natural environment. This method has become increasingly important as researchers strive to understand the delicate balance of our planet's atmosphere while minimizing human impact. A notable recent finding from the Carruthers Observatory highlighted that the geocorona may be denser than previously thought during solar maximum periods, when solar activity is at its peak. This revelation opens new avenues of inquiry into how these variations affect satellite operations and communications. Fascinating patterns and emerging insights. Moreover, the intricate patterns observed in the geocorona reflect broader cosmic phenomena that transcend our planet. The influence of the solar cycle, a roughly 11-year cycle of solar activity, is felt across the entire solar system. Enhanced solar wind during solar maximum periods not only affects Earth, but also has implications for the magnetospheres of other planets. By studying the geocorona, scientists can draw parallels with other celestial bodies, leading to a deeper understanding of atmospheric processes throughout the universe. For example, the similarities between Earth's geocorona and the atmospheres of exoplanets in distant solar systems not only pique scientific curiosity, but also inform our understanding of potential habitability beyond Earth. The role of NOAA's SWFO-L1. In tandem with NASA's efforts, NOAA's Space Weather Follow-on, SWFO-L1 satellite, is enhancing our understanding of space weather. Positioned at the Lagrange point 1, L1, It maintains a constant view of the sun's activity and provides real-time data on solar winds and cosmic radiation. One might think of it as a sentinel in our cosmic backyard. The SWFO L1 mission plays a critical role in monitoring solar events that can impact Earth, such as solar flares and coronal mass ejections, CMEs. These phenomena can have dramatic effects on our technology, disrupting satellites, GPS systems, and even electrical grids. By providing timely alerts about solar activity, NOAA helps mitigate the risks associated with these cosmic events. It's fascinating how interconnected these missions are. The data from SWFO L1 will complement the findings from IMAP, creating a more comprehensive picture of the geocorona's behavior and the broader solar dynamics. As we uncover these scientific truths, we not only enhance our understanding of our own planet, but also inform future explorations of space, preparing humanity for what lies beyond our atmosphere. Cultural practices through a scientific lens. This intersection of science and culture brings us to consider how ancient civilizations adapted to their understanding of celestial phenomena. Many societies built structures aligned with celestial events, such as the solstices and equinoxes, reflecting a deep-seated relationship between their cultural practices and the cosmos. Take, for example, Stonehenge. This prehistoric monument is not merely a construction of stone. It's a testament to the ancient understanding of solar patterns. Archaeological studies have shown that its alignment corresponds with the movements of the sun, suggesting that it served as a ceremonial site for ancient peoples to observe celestial events. Interestingly, modern science reveals that these alignments may have also had practical implications for agriculture, as ancient communities could predict seasonal changes based on solar positions. The marriage of ancient practices with modern scientific discoveries highlights a rich tapestry of knowledge that transcends time. Final thoughts: the continuous quest for knowledge. As we continue to explore the wonders of the geocorona, the scientific revelations from missions like IMAP and SWFO L1 remind us of the intricate connections between our planet, the Sun, and the universe. Each new discovery reshapes our understanding, revealing layers of complexity that were previously hidden. This ongoing quest for knowledge not only fuels scientific inquiry, but also deepens our appreciation for the legacy of ancient civilizations. Their observations and interpretations of celestial phenomena have laid the groundwork for the scientific methods we employ today. In the spirit of curiosity, we find ourselves at the crossroads of history and modern science, where each question leads to new revelations. As we look forward to the insights that will emerge from the geocorona and our solar interactions, we are reminded that the universe is a vast and dynamic place, one where ancient wisdom and modern discoveries continue to intertwine, unveiling the exhilarating story of our existence. At this point, we will unpack more about how these scientific missions can lead to practical applications for our technology and lives. Stay with us as we delve deeper into the fascinating interplay between the cosmos and our everyday experiences in the next segment. Did you know that Earth's atmosphere extends far beyond where we typically think it ends? In fact, it stretches millions of miles outward, blending with the solar wind and forming a protective bubble around our planet. This completely changes how we understand not only our atmosphere, but also our relationship with the cosmos. Here's what scientists actually discovered about the interplay between Earth and space through missions like NASA's IMAP and NOAA's SWFO-L1. As humanity's gaze shifts toward the heavens, missions like NASA's Interstellar Mapping and Acceleration Probe, IMAP, and NOAA's Space Weather Follow-on, Lagrange 1, SWFO-L1, are at the forefront as our quest to understand the invisible forces that shape our environment. These sophisticated instruments are designed to investigate the boundaries of our solar system, mapping the intricate interactions between solar winds and the Earth's magnetic field. But what does this mean for our understanding of ancient cultures and their practices? To grasp the essence of how modern science informs our understanding of the past, let's journey back to ancient civilizations that existed long before we developed sophisticated technology. Cultures such as the Maya and the Greeks were astute observers of the cosmos. They crafted calendars and navigated based on celestial bodies, but they lacked the scientific framework to fully explain the phenomena they witnessed. For instance, the Maya had a deep understanding of solar cycles and eclipses, which were intertwined with their cultural practices. Yet their explanations were often steeped in mythology rather than empirical science. Recent advancements, particularly through missions like IMAP, provide us a lens to reinterpret these ancient observations. IMAP will map the heliosphere, the vast bubble created by the solar wind, which extends well beyond the planets and into interstellar space. This boundary is not just a scientific curiosity. It has profound implications for understanding cosmic phenomena that ancient civilizations might have interpreted as divine or mystical. For example, solar winds can create auroras, which ancient cultures might have viewed as omens or messages from the gods. Today, we can analyze data from IMAP to understand the mechanisms behind these events, offering a scientific perspective that deepens our appreciation of historical interpretations. As we discuss these cosmic interactions, let's explore the methodologies employed by scientists in the field. The IMAP mission, scheduled for launch in 2025, will utilize advanced instruments to study particles and fields in the heliosphere. This is where the magic of modern science intertwines with history. Archaeological findings often reveal that ancient peoples had a remarkable ability to observe and record natural phenomena, albeit without the technological means to understand them. The way they crafted myths and narratives around their observations provides a fascinating backdrop against which we can place current scientific findings. Take, for instance, the work of archaeologists who study ancient sites known for their astronomical alignments. Sites like Stonehenge and the Great Pyramids were constructed with celestial events in mind. While ancient builders didn't have the instruments we possess today, their meticulous observations resulted in structures that aligned with the solstices and equinoxes, demonstrating a sophisticated understanding of their environment. Modern scientific methods, including satellite imagery and ground-penetrating radar, help us uncover the the precise alignments of these structures, revealing a complex relationship between ancient peoples and the cosmos that was previously obscured by time. But what of NOAA's SWFOL-1? Launched in 2025, this satellite is set to monitor solar activity and its potential impacts on Earth's technology and climate. While ancient civilizations may have interpreted solar flares and wind as manifestations of the divine, we now know that these phenomena can disrupt communication systems, GPS, and even power grids. The sun, once seen as a celestial deity, is now understood to be a powerful force that shapes our daily lives, an example of how modern science reshapes our understanding of historical narratives. This intersection of ancient knowledge and modern discovery raises fascinating questions about how we perceive natural patterns. For instance, the idea that everything is interconnected, something expressed in various cultural practices, finds resonance in contemporary scientific thought. The study of cosmic rays, particles that originate from outer space and interact with Earth's atmosphere, underscores this interconnectedness. As scientists analyze data from IMAP and SWFOL-1, the patterns reveal not only information about the solar system's structure, but also potential impacts on Earth's climate. What once seemed like isolated events in the heavens are now understood as part of a complex system that influences life on our planet. Returning to the ancient world, the Greeks, with their rich mythology, believed in celestial beings that influenced human affairs. They constructed elaborate stories about constellations and their movements, which were central to their cultural identity. Yet, as science has progressed, we've come to realize that these celestial patterns are governed by physics and laws of motion, eloquently described by Newton and later by Einstein. The ancient observations that inspired mythos now serve as a springboard for scientific inquiry. But there's more to this story. As we explore the methodologies of archaeology and space science, it's essential to recognize the interdisciplinary approach that modern researchers are embracing. By integrating fields such as anthropology, history, and astronomy, scientists are uncovering insights that would have been unimaginable in the past. For instance, through the examination of ancient texts and artifacts, researchers can contextualize the data retrieved from space missions, creating a rich tapestry of understanding that highlights the continuity of human curiosity. Consider the patterns that emerge when we analyze solar cycles in relation to historical events. Researchers have found correlations between periods of solar activity and significant climatic shifts in human history. This connection is particularly intriguing when we consider the rise and fall of civilizations. For instance, the Little Ice Age, which occurred from the 14th to the 19th centuries, coincided with a period of decreased solar activity known as the Maunder Minimum. By utilizing modern satellite data alongside historical records, scientists can draw connections between solar phenomena and their effects on agriculture, population migrations, and social structures. Delving deeper into the archaeological realm, we find that ancient cultures often crafted their social structures around their environments, influenced by the celestial cycles they meticulously monitored. For example, the Inca civilization of South America revered the sun as a critical deity, evident in their grand temples and agricultural practices aligned with solar patterns. The agricultural calendar was deeply intertwined with solar movements, dictating when to plant and harvest. By applying modern scientific methods, researchers can reconstruct these ancient calendars, revealing not only agricultural practices, but also the sophisticated civilization that thrived beneath the watchful gaze of the sun. Now let's pivot back to our present-day scientific endeavors. The IMAP mission and SWFOL-1 are not just technological marvels. They serve as gateways to understanding the universe's complexity. As we harness data from these missions, we're able to paint a richer picture of the solar system's dynamics. For instance, by studying the charged particles emitted by the sun, scientists can better predict space weather events that affect our technology and daily lives. These predictions not only have immediate practical implications, but also echo the ancient understanding of celestial influences on terrestrial matters. As we progress further into our understanding of the cosmos, we also reflect on the role of storytelling in science. Much like ancient myths serve to explain the unexplainable, science today provides narratives that intertwine facts with the wonder of discovery. When we listen to scientists speak about their findings, there's an inherent storytelling aspect. Each discovery is a chapter in the ongoing saga of humanity's quest for knowledge. The IMAP and SWFOL-1 missions represent the next frontier in this narrative, promising new revelations that could reshape our understanding of everything from climate change to cosmic origins. Thus far, we've examined the connections between ancient wisdom and modern scientific discoveries, revealing how our understanding of the universe has evolved. As we build on the foundational insights gleaned from IMAP and SWFOL-1, we find ourselves in a unique position, one where the past and present converge. The methodologies employed in these missions not only inform us about the physical world, but also invite us to reflect on our place within it. In closing this segment of our exploration, let's remember that the pursuit of knowledge is a never-ending journey. The scientific discoveries emerging from missions like IMAP and SWFOL-1 are not just about collecting data. They're about weaving together the threads of history, culture, and modern science into a cohesive tapestry of understanding. As we continue to share these stories, we honor the legacy of those who came before us, the ancient astronomers who stared at the stars and wondered, what lies beyond? Now, imagine what the next chapters in this story might hold as we navigate the thrilling landscape of discovery and innovation. As we delve even deeper into this captivating narrative, we'll uncover the threads that connect us to the cosmos and each other, leading us into the final part of our journey together. Stay tuned as we venture further into the remarkable relationship between ancient knowledge and contemporary scientific breakthroughs. As we draw our journey through the cosmos to a close, it's remarkable to reflect on how our understanding of the universe has been radically transformed by innovative projects like NASA's Interstellar Mapping and Acceleration Probe, IMAP, and the Carruthers Geocorona Observatory, in collaboration with NOAA's Space Weather Follow-on Lagrange 1, SWFO-L1. These missions are not merely technological marvels, they are gateways to understanding the very fabric of space and the intricate dance of solar and cosmic particles that influence our planet. Let's start with IMAP, which is set to launch soon with the ambitious goal of mapping the solar wind and its interactions with the interstellar medium. What makes this mission so captivating is its duality. It's not just about understanding solar particles, it's about deciphering how these particles influence everything from our climate to the very air we breathe. With advanced instruments designed to capture a multitude of particles, like protons and heavy ions, IMAP will give us a high-resolution view of the heliosphere, the bubble-like region of space dominated by the solar wind. This could lead us to unprecedented insights into how cosmic rays affect our atmosphere and ultimately our technology. But what about our own atmosphere? Enter the Carruthers Geocorona Observatory, which is set to provide a continuous and detailed view of the geocorona, the outermost layer of Earth's atmosphere, which is illuminated by sunlight. This geocorona, composed of hydrogen and helium, plays a critical role in the interaction between solar winds and our magnetic field. The insights gleaned from this observatory will allow scientists to understand how solar activity can disrupt communication systems and satellites, a phenomenon we experience during solar storms. Imagine having the ability to predict these disruptions more accurately, significantly enhancing our preparedness for the future. Now, let's not forget the complementary role of NOAA's SWFO-L1, stationed at the Lagrange Point 1. This observatory acts as our vigilant sentinel, monitoring solar wind conditions in real time. By providing data on solar flares and coronal mass ejections, SWFO-L1 will not only contribute to our understanding of space weather, but will also tie into IMAP's mission by providing context for the cosmic phenomena observed. This interconnectedness of scientific missions is a beautiful illustration of how knowledge builds upon itself, forging a path from raw data to concrete predictions that can protect our technology and our way of life. As we piece together these cosmic puzzles, the implications extend beyond the immediate scientific community. They resonate throughout society. For instance, the importance of understanding solar winds and cosmic radiation cannot be understated in our increasingly digital world, where satellites are vital for communication, navigation, and even climate monitoring. A deeper comprehension of space weather can help us safeguard these technologies that many of us rely on daily. Much like how ancient civilizations learned to read the heavens, allowing them to navigate and plan their agricultural cycles. In contemplating the broader significance of these discoveries, we must also consider how scientific progress teaches us about ourselves. Each new mission, each observation made from our earthly vantage point reveals not just the complexities of the universe, but also our place within it. The knowledge we gain from studying the geocorona and solar winds allows us to appreciate the delicate balance of forces that sustain our planet and, by extension, our civilization. Furthermore, these missions serve as a reminder of the importance of collaboration in science. Scientists, engineers, and researchers from various disciplines are joining forces to tackle questions that interest not just their own fields, but humanity as a whole. This collaborative spirit fosters an environment ripe for innovation and discovery, reminding us that while we may be explorers of the cosmos, our greatest achievements often arise from working together in the pursuit of knowledge. To think about what lies ahead, consider this: the data from IMAP and the subservatories like Carruthers will not only deepen our understanding of the solar system and its relationship to the universe, but also inspire future generations to pursue careers in science and engineering. With each discovery, we plant seeds of curiosity, encouraging young minds to wonder about the universe and our role within it. As we conclude our exploration of NASA's IMAP, the Carruthers Geocorona Observatory, and NOAA's SWFOL1, let's take a moment to appreciate the journey of knowledge that has brought us to this point. The work of these missions serves as a testament to human ingenuity and our relentless curiosity about the cosmos. Each finding enriches our understanding and opens new pathways for inquiry, illustrating that science, at its core, is a never-ending quest for understanding. In closing, remember that scientific exploration is not just about facts and figures. It is about curiosity, discovery, and the stories we tell through the lens of evidence. As we look toward the stars, let us be inspired by the potential that lies within our reach. The universe is vast and filled with secrets waiting to be unveiled, and with each mission, we are one step closer to uncovering those mysteries. So, let's stay curious, keep asking questions, and continue this incredible journey through the cosmos together. After all, the next big discovery could be just around the corner, waiting for us to embrace it with wonder and awe.